Okay, so this is the final part of probability. So we're going to look at conditional probabilities with Venn diagrams, going to look at using probability formulae and a couple of examples with that, and then finally tree diagrams. For some of it, I'm just going to use print offs of my PowerPoints just because I thought it was a bit easier, but we won't be able to do that for all questions at the moment. So A and B are two events such that the probability of A is 0.55, probability of B is 0.4, and the probability of A intersection B is 0.15. Draw a Venn diagram showing the probabilities for events A and B. So event A and event B, the overlap 0.15. So this part of A is 0.4 and this part of B is 0.25. So let's just check. So that adds up to 0.8. So outside is 0.2. So that's part A. Part B. Find the probability of A given that B has happened. So if I know that B has happened, it means I'm looking at that whole circle. So it's out of 0.4. And the probability that A happens is 0.15, which is 3/8. B part 2, find the probability of B given that either A or B has happened. So the probability of A union B is all of this part added together, which is 0.8. So out of 0.8, the likelihood of B occurring is a 0.4 chance. So given that I know that either A or B has happened, I've got a half chance of being able to say that B has happened. And then finally, the probability of A not happening, given that B has not happened. Well, the probability that B hasn't happened is 0.2 plus 0.4, which is 0.6. And within that, the probability that A also doesn't happen is 0.2, which is 1/3. So if B doesn't happen, there is a third chance that A also does not happen. Because A not happening is 0.2 out of a total of 0.6. So we've kind of done conditional probability, just understanding that my denominator is out of what's already happened. So I'm going to now look at actually our given probability formulae for A union B and A given B. And I think a good way of doing that is by using a Venn diagram. Well, I know that the probability of A union B is all of these bits in the semicircle. So I know that this is the probability of A, and I know that this bit is the probability of B. Now when I add them together, I add this bit in twice. So if I want the probability of A union B, I have to take away one lot of that intersection, because A union B is the whole part inside these circles together, but when I add the probability of A and the probability of B, I count this bit in the middle twice. So the probability of A union B is equal to the probability of A, add the probability of B, subtract the probability of A intersection B. Now this formula is given to you, so you don't have to learn it. I can't remember off the top of my head about the conditional probability formula. I think it is given to you. I also think there's this really weird formula that's given to you, and I don't know why you're given it, but anyway. So finding the probability of A given that B has already happened. So again, to demonstrate this, I'm going to draw a Venn diagram. So the probability of A given B. So if B's happened, I know that I'm looking in this circle. So the denominator of my fraction is the probability of B. The probability of A occurring is the part of my overlap, which is the probability of A intersection B. So the probability of A given B is the probability of A intersection B over the probability of B. So both these formulae are really useful for if you're in a situation where you need to figure something out. Usually, in these situations, you're quite often finding the intersection B part. So they're using these formulae in a different way. And we're going to go on to our second to last page. I don't have enough room to draw it on the diagram, so I'm just going to use my paper to do these questions. So on the second to last page, we're looking for example question number 1. So the probability of A is 0.4, the probability of B is 0.6, and the probability of A union B is 0.8. What is the probability of A intersection B? So I know my formula, the probability of A plus the probability of B, subtract their intersection, is equal to the probability of A union B. Probability of A plus probability of B, subtract the intersection, is equal to the probability of A union B. So therefore, the probability of A intersection B is 0.2. Really straightforward. Example number 2. There's actually 3 examples on this page, I just haven't numbered the last one. The probability of A is 0.3 and the probability of B is 0.4. And the probability of neither A nor B is 0.3. Work out the probability of A intersection B and explain what this means about the events A and B. Well, the probability of A not happening or B not happening, so neither A nor B, means that the probability of either of them happening must be 0.7. Because this means neither of them happen. So if I were to draw my Venn diagram, this bit out here would be 0.3, which means that this bit here must be 0.7. So now I can use my formula, probability of A plus the probability of B minus the probability of their intersection is equal to the probability of their union. Well, this means that the probability of their intersection is 0. Well, if the likelihood of things happening at the same time is 0, this means that A and B are mutually exclusive. So they absolutely can't happen at the same time. And finally, example number 3 on this part, before we move on to our very final bit, the really tough probability tree diagrams. C and D are 2 events such that the probability of C is 0.2 and the probability of D is 0.6. And the probability of C, given that D has already happened, is 0.3. Find the probability of C intersection D? Well, I know that the probability of C given D is the probability of them both occurring over the probability that D has already occurred. So therefore, 0.3 is equal to the intersection over 0.6. So therefore, the intersection is 0.18. B, I'm going to stick with my other colour because it's more interesting. The probability of D given that C has happened. Well, this is the probability of them both occurring, given the fact that C has already occurred. So 0.18 over 0.2, which is 0.09. No, it's not. That's me doing something really wrong. I knew I was taking a shortcut. 0.9, not 0.09. Me making 1 10 times bigger and 1 not. 0.9 is that probability. And finally, of this section C, if I can move my sheet up, the probability of C union D. Well, now I can just do the probability of C plus the probability of D, subtract the probability of their intersection. So 0.2 add 0.6, subtract 0.18, which is 0.62. So as long as you've got these formulae, these questions are really, really straightforward. So we do not have to worry about these kind of questions at all. Probability questions really should be a gift to you on the exam paper, because they really are fantastic questions to get. So, final part of probability, and then we've basically finished stats. Please do let me know whether you need regression. I know Miss Goddard gave it to you for a little bit, but I don't know how much work you might think that you need on it. So let me know, because then I can do a tutorial at a later date. We'll do the mechanics first, because I know you're dying to get back to mechanics. Tree diagrams. So we are still looking at conditional probability, but within a tree diagram. Now, you have already done these questions. Whenever you had a without replacement question, this was conditional probability. Because if I've got the probability of A and the probability of B, this is the probability of A happening again, given that A has already happened. And this would be the probability of B happening, given that A has already happened. So just because we've not seen it in this format, and we would never really write it in that complex format, this is what I've done. If I've got 3 blue sweets in a bag, and I've got 7 red sweets in a bag, I take a sweet and I eat it. Well, if I've taken a blue sweet, the probability of me getting another blue sweet is conditional on what I've already taken. So there's now only 2 blue sweets left in there out of 9 sweets. And red is 7 out of 9. So all of these are conditional because they're conditional on this having already happened. So we have met conditional probability before in that form. So we're only going to do one example, that's all we need. A bag contains 6 green beads and 7 yellow beads. A bead is taken from the bag at random, the colour recorded, and it is not replaced. A second bead is then taken from the bag and its colour recorded. Given that both balls are the same colour, find the probability they are both yellow. So, green bead and yellow bead, and I've just done that really low compared to the amount of space I've got to draw this. So it's 6 out of 10 green beads, 4 out of 10 yellow. I could simplify it, but I'm just not going to. one less thing to think about. So I've already taken a green bead and I haven't replaced it. So I've got 5 left, and I've actually only got 9 beads left in there. I've still got 4 yellow out of the 9 beads left in there. If I take a yellow bead, I've now only got 3 yellow beads out of 9, and I've still got the 6 green beads that were in there out of 9. So it says, given that both balls are the same colour, work out the probability that they are both yellow. So given that I know that they're the same colour, what's the probability they're both yellow? So I need the total probability of it being the same, and then the probability that they are both yellow. So both being the same and both yellow, well, in this case, just the probability they're both yellow is enough to be the probability that they're the same and both yellow. So probability that it's green and green, we go along branches, so we multiply. So 30 out of 90, which is 1/3. Yellow, yellow, 4/10 and 3/9, which is 12 out of 90, which is 2 out of 15. So 2 out of 15 divided by, well, I need to sum these together. So 1/3 add 2/15. And I can just put this straight into my calculator. So 2/15 divided by 1/3 plus 2/15, which is 2/7. So the probability that, given that I know I've got 2 of the same colour, and I've just realised that all my maths is off the bottom there, sorry. So the probability that they're yellow, given that I know they're the same, is the probability they're both yellow over the total probability that they're the same, which is probability of both yellow plus the probability of both green. And that's 2/7. So I know that I've got 2 of the same colour in my hands, I just don't know whether they're yellow or green. So the likelihood of it being yellow, given that I know that they're the same, is 2/7. So you can have a go at the mixed exercises, or just the exercises generally, because actually doing probability trees is sometimes quite therapeutic, because they're quite nice topics to do. But I have provided you with some exam questions for you to do that are probability and normal distribution together. And that is going to be a really useful exercise for you to do. Obviously, if you need some practice first, great. But if not, you are welcome to go straight onto those questions.